Check your live.
Request to all the attendees, we will start in the next 10-15 seconds. If you can all settle down, please. So Ram, I'm starting the session 3, 2, 1. A very warm welcome to all our viewers who have logged in today on the 8th of October for the second season of the IWET series.
Kailash, you are muted.
Kailash, we lost your voice.
Back, and we had close to around 2,000 people who had attended the season 1, and we hope to have an equally successful season 2. So the IWET series will be on the second Friday of every month. So on the 8th of October we have the first one, and every second Friday of the month we will have the IWET series till the end of March 2022. So for the season 2, I would now like to announce that we are extremely pleased to have with us Canada as the country partner for the IWET series. You know, according to the Global Water Intelligence reports, Canada is among the 8th largest, water businesses across the globe. And a lot of technology innovations that have happened in Canada, either in the water supply, water treatment, or the wastewater sector, have been successfully adopted in countries all over the world, and we are very pleased to have Canada with us. And every episode of the IWET series, we will have 1 or 2 Canadian technologies being presented for the benefit for all our viewers. So without taking too much of time for the season 2, I would now like to invite our first speaker for the day, Mr. Qazi Syed Ali, consultant for the Water Resources Engineering at the National Water Mission, Ministry of Jal Shakti, Government of India. He is going to be talking about the water use efficiency improvements that have happened specifically in the beverages industry. Over to you, Qazi.
Good evening, all of you. I'm very thankful that Smart Water has invited me for the speaker as a speaker. And today I'm going to talk about water use efficiency improvement at beverages sector. So that is study that I have conducted as a pilot project for an year. Next slide. This project is about for 1 year. There are basic objective of this study is to reduce the water usage ratio and also monitor and assess the UFRO filtration process that has been used in tertiary treatment in the beverage sector after the ETP in the beverage different plants, to understand that what is the actual efficiency of the ultrafiltration reverse osmosis process. So as a pilot project, I have taken first plant, that is Aminpur plant in Hyderabad. Next slide. So the basic objective of this project is to reuse, reduce, recycle, and recharge. So reuse is that we are using the water usage without any treatment. For example, cleaning process, final rinse water we have used for pre-wash. Reduce is the minimization of the wastage, such as sending the ETP sludge to waste treatment processes. And also PT recycling, that the bottle that has been used for wastewater bottles that has been used for particularly for after the brief is taken. So that what has been used for preparing the t-shirts. Recycle is that whatever the water has been recovered, for example, in the bottle washer or CIP recovery, that can be used in place of raw water. recharge is that whatever the water consumption has been taken by the industry. So at the upstream and the downstream side, so if the water has been collected at the upstream side, some interventions has been taken up by the industry around the plants, for example, rainwater harvesting, sprinkler irrigation use, and at the downstream. And then at both the places they have installed the piezometers, and based on that we have analyzed that that what amount of water has been extracted, what is the level of the water, and how much water has been after the intervention has been gone up by putting the piezometer downstream. So at that comparative study has been done. Next slide. So basically, this is the normally water treatment process for the particular industry of the beverages, where the major intake is from the pond, Manjira pond, from where they have collected the water, and this is the typical water treatment process that you can see, in which there is tube settlers and pressurized sand filters, activated carbon that has been used for removing the pesticide or odor. Then it has goes to different units like a de-equalizer, degasser tower, and protect water has been gone for activated carbon filter, where if the chlorine is free, then it can be use it further for the UV. So this water has been used for two processes, particularly in the this taking the groundwater and or the from the pond used in the treatment. Then it also goes to the units, and also it goes for bottling process, because that beverage industry has their own bottling process unit. So in that, when it goes for getting the water as a byproduct for pulling in the water, filling in the bottles, so this fine product has been used. Next slide. So this is the normal water effluent treatment plant process of that particular beverage industry, where they have normally collection sump, oil grease separation, equalization tank. So what we did when we started this study, we did it stepwise. First we have started the monitoring the WTP, then we have inspected the ETP, because there is two issues that have been coming up while the high hardness has been coming up at the end of the tertiary treatment in UFRO, that has been and also the flux carryover. There is an issue of flux carryover, and there is an issue of hardness, and also the issue of failure of the UFRO, that is not giving us opportunity to reuse excess amount of water. Next slide. So basically, our aim is to reduce water user ratio. What is water usage ratio? It is the ratio of the water intake by the industry and the volume of beverage manufactured. So as much as the water user ratio is low for any industry, it means that they're intaking the less raw water, because and for example, if 1.6 is the water use ratio, so it means that for 1.6 liter of water has been used for producing 1 liter of beverage. So as much as the WUR is low, it will be benefited to us. So our aim is that in that project, our aim is that water use ratio reduction is from we got the water use ratio reduction from 1.42 to 1.36. Though it's not very huge gap, but it gives us it's give us saving of water in KLDs in 1,000. Next slide. So we have recommended before doing the inspection, we have recommended that as per the CPCB norms, that high hardness water from that particular previous industry has not been sent to the CETP. So the CPCB has recommended us to use to go for ZLD phase. For ZLD phase, we have recommended this scheme that you can see on the screen, that second stage UFRO that has been recommended by us, using UFRO, UV, ozonator, and CIP. So CIP is the cleaning process, where mostly generally they were taking around raw water, where we have recommended that at least instead of raw water, you can go for treated water. That saves around 30,000 30,000 rupees per day for the particular consumption. Next slide. So we have followed the basic methodology. First, we did the benefit flow analysis to rectify that what are the issues that has been coming up in the ETP, and if you install new UFRO. We did the water balance, TDS balancing. Also, we did the proposed water balance to understand that whether the water has been available, additional water has been available or required for making it available to the new UFRO system, second stage RO treatment system. So, for example, we have started with the bottling process, where we have seen that in recycling unit, where they are using the recycling glass bottles, there is the huge amount of TDS has been generated over there, around 5,000 mg per liter, due to because that recycling glass bottle, and that unit is particularly the bottle washer, where we found that around if we go for, instead of using recycling line bottle line, we can convert it into RGB line, the so that is will be benefited to us. Instead of using RGB, we can go for PET line. So that gives us the reduction of TDS of around 15% and makes the UFRO run up to 80% efficiency. Next slide. Then we move further for analysis of the water treatment process, where we found that since operation, the dealkalizer units results have issues with the effluent TDS, because the TDS is generated very high. And so what we have suggested that we can use the chemical coagulation unit at the maximum output. For that, for bringing the maximum output, we have used the standby 3 micron filter and UV to make the coagulation system run at the maximum output to supply water that has been coming from the PET line directly, to reduce the burden on the dealkalizer unit, and also reduce the chemical consumption. So next, what we did, we also found that there is a possibility of carry of flux into sand and carbon filters, that damaging the filters. So what we did, this analysis we did in the water treatment unit. So we have changed the dosing point for CO2 for instead of using it after the pressurized sand filter, we changed the dosing point for the CO2 before the pressurized sand filter, to get the formation of soluble carbonates and reduce the flux and help in TDS reduction in the pressurized sand filter, that can be taken care in the backwashing. So next slide. Then we have moved towards ATP performance evaluation. We found that both the equalization tank, the water was very dark. This shows that the proper DO level is not maintained, and the DO level we found around 1.5, and COD was inlet was around 1300 mg per liter, and BOD was 1700 mg per liter. So we have suggested that, and we have implemented. We did the repair work for the air diffusers for the equalization tank. We have installed the new diffuser grid system in order to maintain the DO level of around 2 mg per liter or more. Second, we also seen that the aeration tank, also there is an issue of black water due to dead bacteria has been present in bulk, and spent carbon is also coming up. We also found that in aeration tank also improper and adequate air distribution was there. So we have recommended new air blowers in that, and we have placed the new air diffusers for that the capacity of around 1,000 meter cube aerated water that can be supplied, and 50 more air diffusers has been used with the oxygen usage of around 1.5 kg of BOD, and that has been maintained. The DO of around 4 to 5 ppm. So this intervention has been we did in the ETP. Next slide. Also, we have checked the lamina clarifier, where we found that the lamina clarifier, the turbidity was around 50 NTU, that was 20 NTU, that was fine because it was designed for 50 NTU. However, in order to improve the more turbidity, we have gone for the, instead of using alumina based coagulant, we have gone for the iron based coagulant, and that has given the turbidity of around 2.30, and it has reduced the carrier of the flux to the sand filter. Moreover, we have seen that the RO membranes are suffering scaling due to hardness that coming from the feed water, and also we have seen that the hardness is around 50 mg of calcium carbonate, and but the TDS was around 240 ppm, which was hard as compared to when it comes to the UFRO system. So what we did the TDS balancing, and wherever the membrane is getting the high TDS, we have recommended that that lines has been segregated. Membrane cleaning has been done by using sequence of the low pH cleaning first and then the high pH cleaning first. Earlier the reverse order was followed, and this is further have recommended to reduce the precipitation of that in the membrane. Next slide. So this is the proposed water balance where we did the new water balancing, and we found that around 120 KLD. Instead, when we did the water balancing, we found that around 172 KLD water should be available for installing the second stage UFRO for going for the ZLD. But we found that around in new water balancing that around 120 KLD water should be go to the PTL. That is the in Hyderabad, that is the CETP. Next slide. So we also did the TDS balancing, and we found that the certain places where the TDS has been, that is the worst case scenario TDS balancing we did, where found softener regeneration is contributing around 12,000, DL cleanser regeneration is around 8,000, and UFRO rejects around 5,000. So what we did, we have after the TDS balancing, we all these points were like, for example, softener regeneration, this bottle washer, and DC regeneration. So we have segregated these lines. Next slide. So we did the segregation so that all the hardness will go directly to CETP instead of going into the ETP until and unless the rectification has been done. So we have also segregated the high and low TDS lines, also having the additional, we have put the additional tanks near the decausterizer and de-equalizer unit to achieve the segregation, and to stop the high hardness water into the ETP until and unless rectification has been done in UFRO and second stage UFRO has been installed. So this has prevented the UFRO membrane failure and has made the UFRO run up to 70 to 50% efficiency. Next stage. We have also did the small study, that is water use reduction opportunities and Aminpur plant, where wherever there is a raw water intake, what we did, we use the UFRO treated water in that places, for example, conveyor lubrication, and these are the whatever the line has been mentioned in the red, that has been was at that time that was pending, that is still under the constitution, line has to be provided. And there are few places where we are able to make the use of treated UFRO water instead of raw water. Next slide. So this is the graph that shows the UFRO utilization water and non-UFRO. So that has been seen that through the graph that utilization of UFRO is maximum in the cooling towers around 120 KLD, and where raw water has been used mostly in decausterizer backwash. So this is the graphical comparison we did. Next slide. Where we found that around when it comes to the compliance, that 66.66% UFRO treated water compliance has been going on, non-usage compliance around 33%. This is giving us around amount of water that has been recovered in a day is around 333 KLD. And we have found that if the most of the lines where the treated water is raw water has been still using, if they reuse it with the UFRO water, that gives us the more water user ratio, and that maybe increase the efficiency around 60 to 90%. Next. So this is the plan that we have recommended while going to a new ETP UFRO unit. But before that, we have also seen that additional there is a requirement of additional because as per the guidelines of the State Pollution Control Board, that 120, 130 KLD has gone to ETP, and we are still and for one we still want to make up for 172 KLD. So we have recommended all these recommendations, and based on that recommendations, we are able to achieve a small amount of water use efficiency improvement from. So, and this is the scheme that we have recommended at last. If you in future, if the plant goes for ZLD phase, so this will be the scheme where you have to that the plant has to follow. Next. Thank you.
So, Kazi, thank you for this presentation and sharing the findings of this project. We have a few questions that I will take up now from people who have been seeing this presentation. So, Kumar Gay is asking a question. He's saying, can I know what is the ROI of this pilot project? And two, he's asking, what is it that motivates the beverages industry to move towards this pilot project? Is it rising utility bills or new regulations?
So sorry to interrupt. Your voice is.
Okay,
I'm
so
not
we
able to
have
hear
a question
more
from
clearly.
Desaja Kumar Gay.
Yeah.
He's asking a question. Can you tell us what is the ROI of this pilot project? And he's also asking, what is it that motivates the industry to move towards these pilot projects?
So for particular beverage industry, where the water is one of the major component for their byproduct, so that particular guidelines has because as far as I know, that at that time high hardness water has been going to CETP, that common effluent treatment plant. So SSB has issued the guidelines to that particular beverage industry that you should go for ZLD phase if you not control your high hardness water, hardness in the water. So they are not motivated, but they are forced to implement ZLD phase at that time.
So Dilip Chatwal is asking this question: how do you have to control the growth of algae?
Pardon?
Dilip Chatwal is asking a question: how do you control the growth of algae in maybe the ETP treatment during
the growth of the algae in the ETP, for example, if we found that algae growth is very high, so what we did, we have made the proper circulation of water in that particular ETP, that in order to maintain the good amount of DO level, and also we do the mechanical cleaning of that particular ETP if the algae growth has been going on. So manual, you can see the cleaning we did. Then also we look after that how much DO and oxygen level has been maintained if the circulation is proper. And also we have to take care that in the previous units from where the water has affluent water has been coming up, there is no carbon, not much amount of flux carryover is there.
Okay, one more question, Kazi, from Atul Mohan. He's saying, what was the total cost per KLD, including sludge management?
Around, I can't tell exact the cost about sludge management, but we see around for particular cost of that particular water that we are using is around 130 rupees per KLD. So around 130 rupees we are paying for 1 KLD. So it's around it's around you can say, for example, if we make improvements and we use raw water for the particular CIP, instead we use treated water instead of raw water, so we are saving around 30,000 or 15 to 20 25 to 30,000 rupees a day for particular that unit, cleaning process unit only. So what the cost has been, there are two plants. Molali plant is paying around 270 rupees per KL, and for taking the water from that nearby water body, and Aminpur plant is using around giving around 130 rupees per KL.
Okay. One more question we have from Wasim. He's saying, what is the ZLD cost per KLD for the beverages industries?
The ZLD cost for particular beverage industry, if we goes for not in terms of KLD, I can tell, but we can tell that it goes around in 1.1 to 2 crore, because when it goes to ZLD, so they also have to add new processes in that. For example, moving with bioreactor, multi-effect evaporator. So it depends that what is how large is your particular treatment plant, or how large is your bottling units are there. If there is a small plant around 5 lines, 6 lines, or 7 lines, so might be the cost of the going for ZLD phase will be low. But if the you can say if there are a big plant like Dasna plant, in Dasna they have a very big plant, so there are 10 to 11 lines have been going on. So they have to design the ZLD, they have to go for ZLD phase, then they have to invest in more than 10 crores, because in that particular beverage industry also have to go for quality of a standard for selecting that treatment units.
So, Kazi, what we'll do is we'll still have a few questions, but after the next presentation, I have kept a 15-minute Q&A session. So I will take the balance of your questions during the Q&A session, so that we will make sure that most of the questions are answered. So
Sure, sir.
thank you, Kazi, and I would request if you can be online with us after the next presentation. We will again take up the Q&A, please.
Sure.
So moving on to our next presenters for today, we have the topic is on leachate treatment with sequencing batch reactor, and we have Mr. Mohit Malani, Managing Director, and Varun Kaul, who is the project and process leader at Premier Tech Water and Environment in India. So Premier Tech is a leading company from Canada, which has been in India for quite a long time. And over to you, Mohit, now.
Yep, thank you, Ram. So if someone can share my presentation. Right, thank you. Just a small introduction to Premier Tech Water and Environment. We are a leader in decentralized and centralized wastewater treatment solutions around the world. Next slide, please. Our objective is really to play the part and to preserve and improve the health of our planet and its inhabitants. And this is the core objective which all our team members at Premier Tech Water and Environment live by. Next slide, please. Our main expertise is into wastewater treatment, rainwater harvesting, stormwater management, liquid storage, and we've also now started getting into organic waste management. And of course, what goes and binds all of this together is client solutions. Next slide. We are present in 3 continents, 11 countries, and we have a total of 1,326 team members. Next slide. We have a global turnover of now this year, we'll be touching close to 200 million Canadian dollars. And we've been growing at 27% compounded annual growth rate in the last 20 years. And we've completed 10 acquisition projects in the last 12 years. Premier Tech believes strongly in being local. And that is the reason why you see a high number of acquisitions, is that we want to be a global player, but with local presence. So we really believe in the motto of being local. Next slide, please. So just to give you an idea of where our partners and where we are present, we have our own manufacturing facilities in India, UK, Germany, Portugal, France, Canada. And the yellow marks are all partners we have who are manufacturing our products and integrating our technologies inside. Next slide, please. And one more thing which we have, which is part of our DNA, is that we invest close to 3.7 million Canadian dollars in innovation every year. And innovation is not only in technologies, but it is on the terms of our offer, our services, And the most important thing is improving the product life cycle and improving wastewater treatment. Next slide. So this is some of our brands. So EcoFlow. Next slide. I'll go into the details of each brand before I hand it over to Varun for the Leachate case study. Next slide, please. So of course we have on-site wastewater treatment for individual homes. Next slide. Which is the EcoFlow, where we have sold more than 450,000 systems worldwide and is our leading product for Primatech worldwide. Next slide, please. Then, of course, we have our on-site wastewater treatment, which is our big commercial community CCI projects for hotels, hospitals, and everything, where we have done more than 2,000 projects around the world, including selling technologies for big municipal wastewater treatment plants. Next slide. Of course, we are already talking about the SBR in India, and we've got quite a few projects, and we can really design systems up to 200,000 meter cube per day or 200 MLD. Next slide. And of course, client solutions also is something which is very important to us. Next slide. So this is, our expertise. We do design, after-sales support, and maintenance services. Next slide. And yeah, next slide. This basically, trained by experts and everything. So just to give you a background of our progress in India. We've been active in India since 2006, where we have been promoting SBR, and now recently we've launched our own MBR, where we manufacture the media ourselves, our own membranes, and of course now we've also launched tertiary treatment systems with disk filtration. We have commissioned more than 50 wastewater treatment plants with EPC players, ranging from the capacity of 100 KLD to around 32 MLD, and we would be commissioning our biggest STP hopefully by March, which would be of 136 MLD capacity. And we have more than 45 projects in hand which we need to execute in the coming years. Next slide, please. So I just now hand it over to Varun, who will give you on the background on leachate treatment and how we can treat leachate with our SBR systems. Thanks.
Yeah, thank you, Mohit, for the introduction, and thank you, Wastewater team, for giving us the chance. Next slide, please. So we are talking about leachate treatment using SBR technology, sequencing batch reactor. Before that, just giving you a brief about what SBR is. SBR is a sequencing batch reactor. It's a special type of activated sludge process where the entire treatment happens in a single tank. Like anoxic zone, aeration zone happens in one tank, and the clarification also happens there only. We don't need a clarifier, and we can avoid equalization tank also. Next slide, please. Yeah, so giving you a comparison between SBR and a conventional system. In a conventional system, like we need to have an equalization tank and then some pre-treatment of chemical separation, anoxic tank, aeration tank, clarifier, and the sludge system. Whereas in SBR, we just need a SBR system and a sludge dewatering system. So our anoxic zone and aeration zone and clarifier, all three gets combined into a single tank. So that's how we save space, and we can do we can get better quality of water at a smaller area. Next, please. Yeah, giving you more details on SBR tank. So the SBR zone is divided into two tanks, a pre-zone and the main zone. It's divided by a baffle plate, so the water moves from the underflow to the main zone from the pre-zone. We have diffusers in the entire tank, which are fine bubble diffusers used to mix oxygen into the water to maintain DO levels. And then at the end, we have a decanter. In this picture, we are showing our proprietary product, Swing Canter, which is a floating decanter. This works without any power consumption. Next, please. Yeah. So what are the process which happens in an SBR tank? First is filling of the water into the tank. there are two steps to it. Half of the tank, partial tank we fill using without mixing it with air. Kind of anoxic zone or anoxic environment is created. For the rest partial half, we switch on our blower and the mixing happens to create a aerobic zone. And then aerobic zone continues once the tank is filled, the mixing happens, aerobic bacteria does their work in breaking down the BOD and other parameters. Post that, we go to a settling zone where the tank, again the same tank acts as a clarifier, the sludge settles down and the clean water can be taken away from the top. That's next step of decanting zone. So we are taking the clean water from using the help of a decanter, and the settled sludge at the bottom can be recirculated back and can be taken out for the sludge treatment further. Next, please. Yeah. Coming to a leachate, what exactly is a leachate? It's a chemical it's a wastage which forms in the landfills. Once we keep on dumping our garbage on the landfill, the water passes through this landfill, gets mixed with the various type of impurities, goes into the earth with impurities and chemicals, and starts building up dirty water on the earth surface. So that's what a leachate is. Next, please. Yeah. So depending upon the age of the leachate, we divide the parameters thumb rule basis. So let's say if the landfill is young enough, less than 5 years, or the landfill is between 5 to 10 years or more than 10 years. Based on the age of landfill, we divide it. You can see the pH starts increasing, COD starts reducing, our BOD to COD ratio, the biodegradability of the water starts reducing, TOC to COD ratio starts increasing, our organic matter into the wastewater starts reducing, heavy metal starts increasing, ammonia first starts increasing a bit and then comes down again. So that's how the leachate water behaves with the passage of time. Next, please. Yeah. And how does SBR helps in leachate treatment is we reduce in BOD, COD, ammonia, phosphorus, all these parameters we can reduce. It helps us to tolerate peak flow and shock load of BOD, variations of the BOD, whatever happens with the age of leachate. The primary clarification, biological treatment, secondary clarification, all can be achieved in a single vessel, as I told you earlier. And the best part is operation flexibility and control of effluent discharge. So in case we are not getting the peak load, we are not getting the design load, still we can operate the SBR system. Next, please. Yeah, going into further detail of what reactions happens in a SBR tank. First, talking about BOD removal. BOD removal, let's say the COHNS, which is the organic waste into the water. COHNS is like carbon, oxygen, hydrogen, nitrogen, sulfur, all put together, termed as organic waste, gets mixed with oxygen, nutrients, and bacteria present in the water to generate carbon dioxide, ammonia, and new cell tissues. So, and then the indigenous respiration happens of the new cell tissues which are formed in the form of C5H7NO2, get mixed with oxygen, which we are supplying through diffuser and the blower, to generate CO2, water, and NH3. Next, please. So we broke down BOD into nitrogen compounds, and then we do nitrification and denitrification to break further the nitrogen. So here ammonia gets mixed with oxygen in presence of nitrosomus bacteria to generate nitrate and hydrogen and water. The next step is nitrates combined with oxygen in the presence of nitrobacter to generate nitrites. So we are further converting our BOD to nitrogen compounds and then nitrogen compound to nitrites. In this process, we are using BOD and oxidizing ammonia. The values a bit. 4.57 gram of oxygen is consumed per gram of ammonia oxidized to nitrate. Nitrification ions lower the pH by consuming alkalinity at the rate of 7.14 gram of NO3. Okay, it requires DO of 2 mg per liter. Yeah, next please. Then going to, yeah, next please. Yeah, so going to denitrification now. So nitrate, which is generated, gets combined with BOD from the feed to generate nitrogen gas and CO2 as again a gas and water. So this is an anoxic zone which happens where this reaction happens, kind of in the filling time of the SBR system. So theoretically saying roughly 2.86 gram of BOD is needed to complete removal of 1 gram of NO3N. Okay, and denitrification further produces alkalinity at the rate of 3.6 gram per NO3N of reduction. Next, please. Yeah. And then in case we require with all this reaction, if there are some other challenges in the water, we need to do some pre-treatment. In terms of pH neutralization, we prefer to have pH in a range of 7 to 8. If that doesn't, that is not achieved naturally, we add some external chemicals to maintain the pH values. We may have to add carbon source in case the BOD levels are not matching to maintain the BOD phosphorus and nitrogen ratio. So we add carbon source like molasses, methanol, glucose. Next, please. Yeah. Nutrients. We might need nutrients for healthy bacteria, because if the bacteria is dying or dead, they come to the surface in the form of foam. So we need healthy bacteria, and we add nutrients to maintain the health of bacteria if we are not getting enough nutrients in the feed water. If there are toxic metals into the waste, we have to remove them via process of coagulation and flocculation. We can use alum sulfate and coagulant polymer to achieve this, to remove the toxic metals. Next, please. Yeah. So running you through a typical process flow drawing, how a leachate treatment looks like. We have an equalization tank and then a metal separator in case we need it, in case there are heavy metals into the water, where we need lime dosing and polymer dosing as coagulation and flocculation. After this, in case we need, we have a pH adjustment system, and then it goes to the SBR. As I told you earlier, if we do not need these pre-treatments, we can avoid equalization tank also. And then going from SBR, the cycles happen, filling, reaction, settling, and decanting. From there, we get the treated water going into the treated water tank, and then tertiary treatment in terms of let it be test filter, let it be multimedia filter, or anything depending upon the requirement. And sludge can be treated further in a separate line through a filter press, centrifuge, based on the requirement. Next, please. Yeah. So there's a case study of the recent treatment plant which we did on leachate treatment. in Tubre, Mumbai. Okay, so there was Premiertic designed a system for their requirement. We did complete engineering and supply and commissioning of the plant. This plant consisted of equalization tank, flash mixer, flocculator for heavy metals, tube settler, SBR basin, effluent chamber, MCC blower chemical room, sludge holding system. Next, please. A view of the plant. Next, please. Yeah. So the parameters which we were able to achieve post stabilizing the plant, the influent parameters, you can see the BOD, CODs were pretty high here, 1000 to 3000. TS is in a range of 500, and we were able to achieve very good quality of water. Next, please. A bit of design basis. The HRT we maintained here was roughly 5 hours with a SRT of 5 days, with a SRT of 25 days, MLSS of 3000, F/M ratio of 0.12. Next, please. Few more pictures showing our floating decanter. Next, please. Yeah, so I would like to conclude this by quoting this, that we do not inherit the earth from our ancestors, but we borrow it from our children. So we'll keep this in mind. Next, please. And that's why we should preserve it, so that our loved ones are proud of our legacy. Next. Thank you. Thanks a lot for your time. Please let me know if you have any questions.
So thanks, Varun. We do have a lot of questions that have come up in the Q&A box. And what I will be doing over the next 15 minutes is try to take all these questions that have come for.
Kailash, your voice is low.
I said we have a lot of questions that have come into the Q&A box. And over the next 15 minutes, what I'm going to do is I'll try to take as many questions as possible for Varun, Mohit, and to Kazi. Varun, the first question that I have from Himanshu Shekhar is he's asking what type of a reactor is used for SBR? Varun, this question is for you.
Yeah, so we can use a civil reactor tank, or we can use a metallic tank also. Depending upon the flow, we can decide that.
Okay.
If I understand correctly, he's talking about the tank.
He's saying what type of reactor? So I'm basically assuming it's for the tank.
Yeah. So we can use civil, or we can use a metallic tank also, depending upon the requirement or capacity of the plant.
So Anthony Fernandez is asking this question: how does the decanter separate treated water without power?
So this is our proprietary product, which is a floating decanter. It floats on the top of water. So as the water level changes, the decanter rests on the top of level and keeps on floating with it. So the design is as such, it pulls up the clean water from the topmost surface and then takes it out.
Okay. One more question. This is from Dalip Chatwal to Mr. Malani. He's saying how much MLSS is there in the aeration tank? Maybe you, Varun or Mohit can take this question.
I think Varun will be better to answer that right now.
Yeah. So we showed this for this particular requirement. We were maintaining MLSS of 3000, but in general, in case of SBR, we can maintain MLSS of 3000 to 4000 roughly, depending upon water quality and other requirements.
Okay, so Varun, this is another technical question from Karthik. He's saying, how do you utilize carbon dioxide generated in SBR technology?
We don't utilize carbon dioxide, gets escaped out. It's a gas. We don't use it.
Okay. We have Mr. Sati Raju. He's asking, Mr. Varun, what is the time for each process in SBR? Okay,
so that depends on the parameters that depends on the design basis, but just giving a thumb rule. Our filling time is roughly 2.4 hours. And then next is reaction time of again 2.4 hours and decant time of 1 hour.
Okay.
Settling is also for 1 hour and then decant of 1 hour.
Okay. Maybe Mohit, this question is for you. It's from Ihab Sahad. She's asking, what is the Capex cost savings when having SBR as opposed to conventional activated sludge?
That's a very good question. And that actually really depends on the size of the project, because the lower the size, the per cost MLD is not as high as compared to. But if you look at, bigger municipal wastewater treatment plants, we are looking at where the plants which are above 20 MLD, we are looking at around 1.2 crores or 1.2 crores per MLD. But if you go to smaller plants, that increases a bit. Like a 1 MLD plant would be the Capex plant, where the Capex would be around 2.4 to 2.6 crores per MLD. So this really depends on the project sizing and different other factors also.
Okay. So Varun, maybe this is a question for you again. Anthony Fernandez is asking, is the SBR a batch process or a continuous? And the second question is, how much time is required to treat if it is a batch process?
I'll just answer the first part of the question. With Primatech, I think this is where we differ from most of our competitors, is that we design the SBR as per the client's requirements or as per the influent wastewater treatment needs. So if necessary, we do an intermediate flow, we do a continuous flow, and it really depends on the project and all the variables which are involved in designing the SBR. The second question I will leave to Varun, but I'll just give another example, the 42.5 MLD SBR, which we have done in China, which is for industrial effluent also from industry. It is a continuous based SBR, but in India, we are doing primarily intermediate flows. Varun, second part of the question is for you.
Yeah, I'm sorry, Kailash, can you repeat the second part of the question?
Let me just, how much time is required to treat it if it is a batch process?
Again, so that depends on the water parameters. All these are very subjective questions. Giving you an example, for this particular leachate treatment, we are maintaining HRT of 5 days. Whereas in general, if you talk about a sewage treatment, we maintain a HRT of 12 to 14 hours.
Okay. So Sridhar is asking this question that the influent BOD is very low in a leachate. What is the maximum BOD that can be treated in your SBR?
For BOD, we don't have a limit. You give us any amount of BOD. If it's a recalcitrant COD and it's a BOD, which is again biodegradable chemical we are talking about, any value we can treat it, not an issue. Maybe the tank size varies depending upon the feed, depending upon the BOD levels, but we can treat any value.
Okay. Pradyumna is saying, you said that the decanter does not require any power. How does it hold? How can you maintain floating in?
Okay, so that's what I was mentioning. It's our proprietary design where the end of the decanter has a hydraulically stable pipe which stays. Giving you a rough example, if you say a float valve, what we use, which keeps on floating on top of water and moves with the water level, something similar to it, what we use.
Okay.
The principle remains same, but yeah, the engineering is different.
So I'll take a few questions to, Kazi now. Kazi, you are there? Hello, is Kazi there? So maybe till Qazi is not there, I'll take a few questions, for Mohit and yeah. So Chirag Hadwani is asking, what is the best technology available for biological treatment other than SBR for textile effluent?
So
Mohit, you
for
want to take
textile
this?
effluent, at the end of the day, it really depends on the kind of textile also. Varun will back me up on this because at the end of the day, textile require with color and everything coming in, you need a physicochemical treatment prior to the secondary treatment or the biological treatment. So it really depends now on clients because textile is also a waste and we have our MBBR which makes it more compact, but the power consumption is higher in an MBBR because the blower is running 24/7. You have an MBR system which we also do, can do a physicochemical followed by MBR, but the problem with MBR is that the capital cost is too large, is too high, and then you have the SBR which gives you the perfect optimization, that the fact that because it's running on a DO mode and on dissolved oxygen, you are able to control the blowers. So your power consumption is lower, but the land is little more than an MBBR, but more than an MBR. So it really now, we need to talk to clients and design systems as per their need because, textile being more private players, we could, there could be land constraints and everything. So this is a very subjective topic per se, but at Premier Tech, we are there to treat your wastewater needs, and we are willing to design, irrespective, we are technology neutral, as we say, and we will design a system which would work for your needs.
Okay, Samir Sharma is asking this question. He says that we can see that you have 5 days of HRT, which is very high. How can you compare the SBR with anaerobic treatment?
So HRT, as I answered in the previous question, in general for a sewage treatment, we maintain a HRT of around 12 to 14 hours. But this being a special type of waste, we had to have high HRT to treat because the biodegradability level of the BOD, COD were pretty low. So to treat it, we had to maintain high levels.
Okay. Wasim is asking this question. Do we require any anaerobic or anoxic treatment for leachate treatment before aeration?
So anoxic is required, which is again a part of our SBR system only. As I told you, the first half of the filling happens without mixing of air. So the partial filling happening into the tank is without air mixing, where we create anoxic environment and anoxic reaction happens. The rest half of the filling, we switch on our blowers and the air starts coming in and the aerobic environment starts developing. So that's how we maintain anoxic as well as aerobic condition in the same tank.
Okay. Mohammad Zamir is asking this question. Can SBR be used in the pharmaceutical industry?
Yes, why not? So SBR is an activated sludge process, which is for reduction of biological parameters. Let it be in terms of BOD, nitrogen, phosphorus, and things. So in case if you have such requirements, definitely SBR can be helpful there. And for if the water is tough to treat, which is not easily biodegradable and other things, we may have to have some pre-treatment and some post-treatment to meet the requirements of the outlet water.
Okay. Wasim is asking this question. How do we manage the treatment and leachate generation flow rate for an SBR system?
Leachate generation flow rate.
So basically, with the site which we did at Navi Mumbai, it was a young leachate field. It was a new leachate. So at the end of the day, there are certain calculations which the consultant and we work closely with the consultant to calculate certain things as to, depending on how young or how old the leachate field is, to know how much leachate would be coming into our system. So that is really again site dependent, because there was one slide with Varun was saying that how we define young, old, and mature mature leachate field. So it's on the basis of that we look at we talk to the consultant and we talk to them and to see, looking at all those parameters and designing the system and the leachate flow.
Okay, we have a question from Mohammed Salah. He says, can you give us a
Your voice is broken, Ram.
Kailash, your voice is broken. Kailash, we can't hear you.
hello?
Yeah, Kailash, tell me please. We couldn't hear the question.
Yeah, we have a question from Mohammed Salah. He says, kindly give us a brief comparison between MBR, MBBR, and SBR.
We can share that with Mohammed Salah. We have a presentation ready and we can share that also. We can share that. We don't have it on handy right now, but we can definitely share one.
Okay, I will share Mohammed Salah's email ID with you. Brajesh Kumar is asking the question, what's the temperature range we should maintain in SBR during aeration?
Temperature for aeration is, so we have bacteria in the tank, right? For that, we need to maintain an ambient temperature for the bacteria to survive. It should be in a range of 15 to 35 degrees Celsius.
Okay. Shivraj Kutwad is asking this question, what is the position of an anoxic tank? Is it before aeration tank or after?
Before aeration tank, it should be generally, but in our case, the entire tank works as anoxic at a time and the entire tank acts as aerobic at other time.
Okay, Ravindra Singh Jankar is asking, what is the function of the pre-react zone?
Yeah, so pre-react zone has better anoxic conditions because the feed is coming into the pre-react zone. So we are getting direct BOD there, which gets mixed with our nitrogenous bacteria, and we can have better anoxic reactions there happening because of the availability of good quantity of BOD, organic waste.
So Mohit and Varun, we do have still a few questions that are there, but I will go as per the agenda and I will share these questions with you directly. Maybe you could answer to the viewers, directly to their email IDs.
Definitely.
Sounds like a plan.
Okay. So thanks Mohit, thanks Varun for sharing this presentation with us.
Thank you for the opportunity.
Moving on to our next presenter for the day, Mr. Sanjeev Shrivastav, the Chief Technology Officer from Action Consultancy, is going to talk about membrane bioreactor, a new life to activated sludge. Over to you, Sanjeev.
Thank you, Kailash. When share screen, anyone can just confirm when my presentation's first slide is visible.
So it is visible now.
Thank you, Kailash. Thank you, Smart Water and Wastewater. Actually, Wastewater reminds me that whole lot of all the waste are getting problematic, and I must congratulate Kailash and your team that you are doing such a wonderful job in organizing such events like Industrial Water and Effluent Treatment webinar series. Thank you very much. And I have a pleasure in talking to you on membrane bioreactor. As I could see, we have more than 300 participants, so it makes me very responsible to talk something very sensible with respect to this technology. Just a little idea about what we do. My company, Action Consultancy, focuses on training and performance management, design, engineering, consultation, condition assessment, retrofit and modification of the existing projects, some kind of pilot studies, innovations, O&M advisory services, chemistry integration with the existing projects, whole lot of project management consultancy for the new projects. In short, we focus on knowledge management in water and water. And what's this water? What is the new word coined by my team, my colleagues? And we believe that all the recycled water is the daughter of water, and it should be named water, pure, pristine, and future. Because in the future, probably we don't have water, we have just water, the way we pronounce water. Here's my team. We have a young team, a lot of microbiologists, organic chemistry experts, chemical engineers, environmental engineering experts, design validation engineers, civil engineers. So this team mainly works on the, with our projects with customer and consultants, and therefore I'm more relieved to attend training programs, talk in webinars, do some training, system kind of lectures. So this team is very, very strong and is willing to serve you all guys. Coming straight to the subject, MBR is not a technology. MBR is a combination of activated sludge process, which is a technology, and filtration, which is the bioreactor part when you say. So the technology lies in activated sludge process. I'm thankful to my colleagues from Premium Aqua, who very nicely covered the COD removal, nitrification, denitrification. So all those slides which you have seen are valid for this part of the word, which is called activated sludge process. And wherever the next process is filtration, where your job is to treat the clean water, take it out from the reactor. My focus more would be today on that area. While these things coming in, we all are familiar with something called activated sludge process. Lots of schemes, influence coming in, then you put some screens, you create some anoxic conditions, maybe anaerobic condition also if the phosphate removal is the goal. You go to activated sludge reactor. Till now, you manage everything. And when it comes to final sedimentation, you start worrying a little bit. And then when you go to conventional activated sludge process, of course, there's an issue with the activated sludge reactor also, but a biologist or a good wastewater treatment expert has got several, ways to solve those issues. But majority of the cases, the final sedimentation and filtration or something called tertiary treatment becomes a headache, and especially when we are looking towards recycling and reuse. So here comes the MBR with the same kind of structure, almost everything same. But what is the difference is you didn't see now the sand filter part or the settler part. So how you can avoid those two things? You can avoid two things by a very simple action called suck the permeate from the existing aeration system. So you are taking, using the energy of pumps on the suction side. The barrier is the way we put something called a screen or something called, a basket strainer at the inlet of the pump to remove the bigger solid particles. Now you have to have something like membranes, which are very, very fine, so that they do not allow any biomass to escape the aeration tank. That's a very simple process. And definitely it has got a lot of advantages. Some advantages we talk about. First, what are the limitation of activated sludge? So most of my colleagues would agree with me, and most of the people who have worked in water and wastewater management have faced the problems of poor settling, floating sludges. Now, both these problems, are interrelated. Poor settling means sometimes the sludge consistency is not coming very good, So the treated water quality is good, but the sludge compaction is not taking place. And floating sludge means, wow, your treated water quality also has become bad and everything goes to the filter. Now look at the filter, what it's doing. Filter is trying to filter everything because it is filled with sand. So it will filter everything. But the biomass which is going to the filter bed now has to remain there in anaerobic conditions. It starts creating problems. And one of the biggest problems it creates is odor. And if the objective is tertiary treatment, maybe a very simple objective like toilet flushing, or maybe a simple objective like gardening, your objective is not met, because once an odor, which is called a gas, is found, after that you will put UF, RO, or whatever you want. Nothing will happen because gases will pass everything. So one of the big responsibility today in wastewater treatment, in sewage management, is how do we develop a process which is neat and clean, which does not produce any odor? Because if odor is there, you are not willing to recycle the water even for washing your car. So this is where the MBR became very, very popular in India and whole world also. And I actually like this technology because this is something, if handled well, can be the one of the very good technology with respect to the recycling object. But there are a lot of advantages we get. Compact because very high MLSs, less surplus sludge production. Yes, because A lot of bugs or a lot of sludge can be again, consumed as a carbon source within the reactor. So you have low biomass production. Excellent quality with respect to BOD. You have seen the previous slides. So the membrane does not allow any kind of microorganisms to go out of the system. So all those microorganisms which were supposed to be good microorganisms, but not doing, and capable of doing some good job, but they were getting washed out of the membranes because of settler. So those kind of biology can be used. And on the membrane side, if you look at advantages, so there's no need to have effluent disinfection, and in fact, water reuse is actually not quite possible. So these are two verticals in which you get the advantage. Be aware, the first vertical, biological and bug behavior, is totally different when you go towards high MLSS environment. High MLSS environment means poor settling characteristics and lots of shit production by the biomass. So you must know how to manage that shit, otherwise you're in problem. Same way, less surplus sludge production looks very advantageous, but that means you are digesting the sludge within the reactor. So lots of oxygen consumption. So be aware of that. So if you're not designing MBR well, you're likely to be in problems. This slide is very simple. MBR, you can have pore size, MF and UF. The pore size has got relevance with respect to 0.01 micron to 0.3 micron. Any MF or UF material can be used by in membrane bioreactor. Different manufacturers use different pore sizes. As it appears very natural, finer is the pure, better is the treated water quality. Okay, but the TMP, transmembrane pressure differential, becomes higher when the membrane is fine. So there is a trade-off between pore size or transmembrane pressure differential. In 15 minutes, I cannot cover everything in MBR, but I'll try to cover the relevant parts. So in MBR working conditions, we have something important called filtration, backwash. We have something important called air separation vessel, pre-filters and basket filters, filtrate reservoir, and which is very important unit. We know where the filtrate reservoir should be, how it should be designed, and lots of manifold valves, because lots of flow and reversal flow has to happen. Now, the two ways you can put the membranes. You can put submerged, you can put pressurized. I'll be slightly faster on some slides. So if you put the membrane tanks in the same kind of tank, it is called membranes in biological tank design. So no recirculation needed, neither supplementary tank. So believe me, it is not an advantage, it is disadvantage. So don't say that no, nothing needed, this is the best. No, when you go learn a little bit more, you will feel that it could be a disadvantage. Membranes in separate tank is much more advantageous, but you require recirculation units. It is required for big plants. So there's several filtration tanks, and it is easy to carry out the recovery cleaning of the membranes because your membrane tank is separated from the biology tank. There's one more modern way to do is that you take a reactor, but all your biomass via feed pumps, take it to the external modules. So if you look at the right-hand side pics, looks very neat and clean, no mess, everything covered, beautiful plants. But it's got its own issues, it's got its limitations here. Everything good is, like for example, automatic cars are good, but the automatic cars have got some their own limitations. If you don't know how to unlock yourself, you remain locked in the car. So the more training, more precision is required in handling something which is more sophisticated. When we look at the effluent parameters, conventional parameters, I'm not going to read BOD, COD. If you look at the MBR, you get very good quality. And believe me, very good quality means very good quality. So what you see here is something in the aeration tank, something in the sludge, and something as a liquid clear permeate product. So you have input, you have aeration tank, and you have a very clean, crystal clear product. The real advantages of MBR comes into three parameters like SDI, coliform, and fecal coliform. Because the other parameter is more biology dependent. It's not MBR dependent. But these three parameters, SDI, coliforms, and fecal coliforms, count to be very low. Or in fact, turbidity also, I'm sorry, I didn't made it green, is all related to the filtration efficiency of the membranes. Now, what are the typical design parameters? So quickly telling BOD, COD, organic loading rates, whatever we have studied in activated stress process, believe me, it is the same process. There will be 1,000 people telling in the world that MBR is a new technology. There's nothing new in the technology except the separation process. The entire old age technology read in McFID is the same technology of biology in MBR. Okay, there's no change in the technology. Yes, the filtration part is totally different. MBR treatment, grit removal is very important because sand cannot go to a sophisticated equipment like, earlier if you have a small water treatment plant, wastewater plant, you can say, okay, let the grit go to aeration tank, it will go to the sludge. But in MBR, don't take that risk because you are pushing some water from the aeration tank to the MBR tank, and the grit and sand cannot go to membrane. It's a very fragile material. Grease is absolutely no going to the system. So some systems will require some kind of primary clarification. Please do that. But the disadvantage will be primary clarification will remove some of the BOD and some of the TSS also, which may be healthy and good for your plant. So I'll come when I talk about case study. And flow equalization is important in MBR. Very, very important word is flow equalization. If you are not doing the equalization of the flow, you will have problems. What kind of problems will come in the future slides. You can use any kind of membranes, but this is technical word. The reality, tubular ceramic membranes are very rare. I have not seen many plants, but there could be some very good application with ceramics. I am developing right now some very special things with ceramic membranes in MBR module. A spiral wound membrane also I have not come across much. No, in fact, I have not come across any spiral wound membrane used in MBR application. But tubular membranes, flat sheet membranes, and hollow fiber membranes are pretty common, and submerged membranes therefore are very common. But there are enough side stream or pressurized application also in the world. In fact, one of the very large installation of anaerobic MBR is done with side stream in pressurized way. Anaerobic, not aerobic. So one of the largest installation in the world, for COD removal in anaerobic is done with pressurized membranes. Now, what we are typically talking about, I don't want to really name a lot of manufacturers, but just there could be some 10, 15 more good manufacturers. Just to give a comparison of 2-3 membranes, Puron, Xenon, which is known as Suez now, Mitsubishi. So we have different material, pore size is different. So you can see first 2 columns are UF and the third column is MF, filter ID, OD, etc. So there are some kind of comparisons. We like all this kind of comparison. And start telling which is good, which is bad. In my 30 years of experience, I said everything is good because it is produced by one of the best world's companies. So there's no comparison on various things. But we are used to compare the cars like Alto versus Hyundai versus Japanese. So we start comparing the same thing into the technical matters also. These all products have been produced by world's renowned companies, and therefore I have respect for all the products, and they are beautiful products. Same is the case with the flat sheet. There are a lot of discussion between whether a flat sheet is good or a spiral wound is good. So you look at the flat sheet membranes, they are beautiful membranes and one can use it. Only sludge accumulation in the flat sheets. If you are doing this because of the poor engineering design, I'll say no problem in the product design. In the engineering design wise, if you have not done well, you will start telling, no, the flat sheet membranes are not good. But otherwise, I've seen many installations in Japan. They are all flat sheet membranes and they are beautiful products. Now this, therefore, is a slide which everybody wants, so I have to give. This is not a comparison or recommendation, but it's an experience. So with respect to parameters like air consumption, high MLSS, complexity, design fluxes, robustness. Now I've got no reason to say that hollow fiber membranes are not robust, but if it is a flat sheet, it's a slightly advantageous when robustness is a parameter. So this is the experience what I'm talking about here. So on and so forth, membrane redundancy, simplicity of the system, and sludge accumulation. So you can say sludge accumulation can be there slightly more in flat sheet, but I have not seen much sludge accumulation in hollow fibers. This is what experience is. Again, I'll repeat, no comparison, no recommendation. This is produced by the world's beautiful companies. This is where the next thing comes is, and this is where the entire attention should come during my presentation. Unlike activated sludge process, which was a continuous process, suddenly the process engineers, please realize now you are dealing with the two processes. One is called continuous process, which is activated sludge, and the second is called membrane filtration, which is a batch process. And the batch also is so small, 9-minute filtration, 1 minute backwash, 9-minute filtration, 1 minute backwash. So we are talking about in 1 hour, 6. So in a day, 150 cycles. Now, can you appoint operators to do 150 cycles? The answer is no. So the backwash efficiency right here Ignorance of a PSF backwash, okay, there's no problem. But ignorance of a backwashing of a MBR membrane means the sky will fall. So the 25% of the problem in the world which we see in MBR systems are related to the backwashing issues. Flux not designed properly or flux designed properly, but sir, what to do? The pump, what we got was 20% less capacity, so we thought it's okay. We will increase the time of backwash from 1 minute to 1.2 minutes, but the pump becomes slightly smaller. So these kind of cutting corners can create problems, and that's where my experience comes in. MBR backwashing leads to 25% of the problems. Almost 20% of the cases, the problem is into deaeration and degasification. Now, many people tell me why deaeration and degasification is required in this particular system. But if you understand the third angle of biology, physics, and chemistry, we are producing carbon dioxide as a gas. And in a equipment from where we are doing something called sucking, we are appointing suction, Henry loss comes to the picture, and gases preferably will go into the fiber. So if the gases go into the fiber, they will create something called gas lock or air lock. They must be degassed or deaeration must take place. If it is not happening, MBR system becomes problematic. So in an engineering design, some people do mistake, maybe some vessels, sometimes people don't do deaeration. They do something called auto air removal at the time of start of filtration cycle, but that's not good enough. For a larger installation, deaeration and degassing phases are must, and proper engineering is required for that. And very rarely, that's why I say only 5% problems are accounted towards something called cleaning strategy. Your membrane cleaning strategy depends upon two things. One, manufacturer's guidelines. Second, your own process waste. So you cannot generalize. In my previous plant, I have this kind of cleaning strategy. So in next plant, we'll have this cleaning strategy, because those two plants could be totally different. So it depends upon membranes. It depends upon the plants. Chemical use are very simple. Chlorine, acids, and alkali. You don't have mega, very, very difficult chemicals. Sometimes a little bit of formulation addition like dispersant and all that helps. Frequency could be municipal wastewater treatment plants. If you do once in a week, it's okay. An industrial wastewater treatment plant, I've seen even maybe you have to do cleaning once in a day. It all depends upon what is the kind of waste is. So all your problems solved. 25% plus 20% plus 5% is about 50%. So if I ask you a question, where is the next 50% problems in MBR? So your answer is not here actually. This is a slide which has come in between. Foam and scums, which you see in MBRs, is not a problem. Okay, if you ask a biologist or if you ask me, I'll say foam and scum are not a problem. You get prepared for it. Because if you want to work with higher MLSS, means high quantity of bucks per cubic foot of volume or per meter cube volume. So I'll use a bad term, then you be prepared to manage that much shit. Because if the bugs are there, they will eat. Okay. And that's their job. They are prolific eaters. So foam will be there, scum will be there. What is required is that you plan for foam. And what is the best way to plan for foam? We all have learned in engineering 300 mm of freeboard. It doesn't work here in MBR designs. When you are talking about 300 mm of freeboard, no, sorry, 1 meter of freeboard in aeration tank, because that's the only way you can manage the foam. Spraying something on the foam is not a good idea. Same is the case with scum. Put the floating skimmer to remove the scum periodically. There's no other way, or you put something called scum guard in the anoxic zone. These are the characteristics of these things. Even we are simple people. Even at our home, if we put some pulses dal with water, next day what we get in the pot? Dal becomes fermented, but you also get foam. So you can't avoid foam when there is a bioactivity. So suppressing that foam by suppressing chemical is not a good idea. So foam and scum is actually not the issue. It is something which will happen, and a good MBR designer will plan for it. The largest issue I see is MBR, which is not properly automated. So MBR should be never without automation. PLC, SCADA, interface, and therefore the relevance and importance of all these equipments, electrical equipments, a lot of instrumentation is often ignored. Believe me, if something has to work in a batch of 150 batches per day, and add 6-7 more different styles of sometimes CIP also into it. It has to be 100% automated, operated from my desk right now here, a plant in Chennai. Something like that kind of environment. If you start leaving it to the operator's intelligence to run an MBR, then it will be a problem. And Shirodkar, my experience has happened, most of the MBR plant I've seen, the major problem is not into membrane, major problem is not into engine design, major problem is cutting corner on the automation part or using the poor quality components. Now we talk about some good things. So we'll talk about a good case study. There's a potato chips manufacturer who has got this kind of waste, TCOD, TBOD. You can see in the bottom, somewhere I'll use my cursor because now I'm going to the navigation mode. So somewhere here, we are talking about this 1,000 and all that. So this kind of TCOD and this kind of COD results are coming. BOD is coming 4,200 to almost 25. Fantastic. How it is possible? Now, when you look at the existing plant of this kind of operations, just to go by the unit names, you have hyperbolic screen which removes potato chips, part and the peel and all those kind of pulps. Go to equalization, pre-treatment, go towards aeration tank, the sewage. Then you go towards the secondary clarifiers, thickeners, scum removal, and all those things. These are some kind of existing plant details which they wanted to modify. So it was modified with the DAF systems. There was one more option, whether we can put a USB, but they concluded to go for DAF. Once they went for DAF and finally went to Anoxic, AT, and MBR, pumping, product, beautiful. So some new unit installed, and this plant is performing superb, that kind of quality which I'm talking about with the respect to the upgradation. So what is the success story on this kind of MBR? Very simple, highly automated plant, nothing else. So if you make a plant highly automated, what is there in the potato chips? It's a beautiful product. There's no chemistry involved into it. It's whatever the COD load is highly biodegradable, so to speak. Now let's talk about one or two bad case studies. The idea is not to blame anybody, just to share the experience. So in one of the instances, you can see that this is an MBR area, but there's an entire plastic film here, right? So one has to avoid, the foreign material getting into something as sophisticated as MBR. But when you look at the engineering side, this is a design of a beverage-based MBR. So the designers have designed. Now, if you look at this table, which is going to appear very complicated, but normal operation, permeate extraction is 31 meter cube, recirculation is 50 meter cube, back pulsing is 0 because there's backwashing. The feed pump has to start at 25 meter cube per hour. So something close to 45 meter cube per hour is the fill rate of the MBR. That means in MBR tank, water is coming at this rate. But suddenly, at the time when the backwash starts, because of whatever automation we have, this pump remains as it is. The backwash pump starts getting on, so it starts pumping water at this particular rate. Feed pump cannot be stopped, so it remains like this. And suddenly MBR starts filling at 131 meter cube per hour. It happens every 1 minute in 9 minutes. So what is the net result? This is the kind of design is called, it was pump to aeration recirculation design in technical terms. So level changes in MBR tank, very common sense. And this level changes where can create a problem. That means there could be overflow at the peak condition, but which has to be avoided. So the simple solution to avoid, somebody followed. And then what was happening is level changes in MBR tanks were resulting in the permeate extraction without full submersion, then nearly 9-minute filtration. So whatever level has increased in the tank, that is you have compensated. Fine. Now next 9 minutes, the filtration rate is more than the fill rate, correct? So the filtration rate will come to a point where the sum of the membrane will start going into the air. Is it allowed? The answer is no. So the simple thing like a little bit of more automation that it should trip, or if the level goes beyond certain level, there should be alarm and the cycle time should be adjusted. These kind of automations, if not built into the automation design, you may result into problem. And the poor operators were not able to really find out what is the problem because they have never seen MBR working in that way. Maybe commissioning engineer, when he was working, it was okay, but when he left the site, it was not okay. This kind of problems happen. One more, case study of a health drink provider. Now, what is the issue? It was the pump to aeration recirculation design again, and they reported the clogging on the flat sheet membranes. Now understand, if the flagship membranes are clogging, the reason is very simple. Poor removal of rejected MLSs from the TSS. Now, what we are talking about, we have to do a proper plug flow reactor design. Simple, very simple thing. Why? Remember, very important thing. A lot of time when MBR is taught, we talk about air scoring. This is a beautiful word. Everybody loves this air scoring. Now remember, air helps you keep surface clean by shear. That's it. Air cannot lift your particle and take it out of the MBR tank. But the responsibility to return MLSs back to activated sludge is that of the designer. And a reactor design should be there in front view. I get a warning of unstable connection. I hope it is improved. Okay. So if you see this view,
2 more minutes.
yeah, I'll just finish. So it's, if you look at the front view or LHS view or top view, you must distribute whatever coming up into a tank very nicely, and they all should rise up or rise down. That is up to your design, but it should look like a more plug flow reactor, which is pumping out the accumulated MLSs. If it is not happening through the entire cross section of your top view, that means accumulation will happen in the areas where the velocities are slightly lower in comparison to the nearby. Very simple. Air will help you clean the surface, but air will not help you to take the rejected MLSs from the membrane surface to the aeration tank. So this responsibility sometimes creates problem. Shirodkar reminded me at the right time. It was my last slide. So, and we keep discussing issues, poor screens, priming issues, automated valves failure issues. You know, sometimes automated valves, those valves are required to be, working how many times? You know, you are talking about 150 times the valves to start open, close, open, close, open, close. So that quality cannot be made in my neighboring industry. The quality has to be somebody good. I will not say made in German because India also makes very good quality. But there has to be quality in the components which you CIP not automated sometimes. Oh, CIP to ek bar karna, then we'll do it manually. So that's it. Thank you very much, and the floor is open for questions. Thank you very much, participants.
Thanks, Sanjeev. I will take a few questions that have come up to you. So we have Samir Sharma.
I'll stop the screen sharing first.
Yeah. So he's asking a question where he says that the cost of an MBR plant is 4 to 5 crores per MLD, and whereas a SBR can cost only around 1 to 1.2 crores. How do you justify the MBRs for medium-sized municipal wastewater treatment plants?
No, it's a very, very commercial kind of thing. So it becomes difficult to answer because the plant which I recently designed is 7 crore per MLD. So it all depends, we talk about something called cost of ownership, and we talk about something called the solution is sustainable or not sustainable. So different agencies have different parameters and on which we evaluate, and a simple calculation like Capex calculation, OPEX calculation. Nowadays, people talk about TOTEX, total, TOTEX. They talk, some people talk sustainability. See, everybody has got its own yardstick. I can simply say that if you want to prove that MBR on cost comparison will be low cost than any other technology, then we are sacrificing automation. And if you are sacrificing automation, then I don't recommend it. So MBR, if you want to afford, it would be the most expensive thing to afford.
Sanjeev, we have this question from Shailesh Patil. He says that MBR membranes are hollow fibers. So what will be the preferred direction of flow, whether it is outside in or inside out?
Good question. MBRs are always outside in when they are submerged.
Okay. Prashanta Biswas is asking this question. What is the lifetime of one membrane and what could be the maximum capacity of MBR?
See, when I started learning MBR, there were not enough installation in India. And most of the plant where I have visited, They were either 7-year-old membranes or 9-year-old membrane, and in one case, 14-year-old membrane never replaced. But when we started developing this in our continent in India, now last 10 years, I have seen many plants which have even failed in 3 months, 8 months, 1 year, and all the blame goes on the membrane. I'm sorry, there is no problem with the membrane. They are all made by the beautiful people. It's the problem in process designing and engineering. I can easily vouch that if I myself have seen 2 or 3 installation in sewage treatment plant. I don't want to name the company in Japan. The membranes were not replaced for more than 13 years. Same first, set was operating for almost 13 years without any problem.
So Chirag Hadwani is asking this question. So what is the maximum capacity plant installed in India based on MBR technology?
Well, I won't be really able to order it, give the answers because I am not a commercial person to do a lot of engineering. I'm more a consultant. So I can say that to best of my knowledge, I have not seen more than 2 MLD in industrial water treatment. That is approximately 75 to 80 cubic meter per hour. I have not seen. And in municipal use of sewage, I heard that the company Degremo did a plant in Cubbon Park in Bangalore a few years back, and there could have been many more plants. I really don't keep a track on the municipal projects.
Okay,
Sorry to disappoint. I could have answered this question, but I don't have the answer.
no problem, sir. Tibuye is asking this question. Does the oil not result in blockage to the MBR? What is the limitation of the oil concentration?
Good question. Very good question. Thank you very much for asking. This is something which was not in my slide. Oil is not a problem. Like if I talk like an Indian, we can always decide whether we'll eat chapati or paratha or puri. But we cannot keep all our food submerged in oil. So typically what we talk about 3 to 10 ppm of oil going to the aeration tank is not a problem at all. What should be avoided is the grease part of it. Oil is not a problem. Too much of grease should not go because grease will, be sticky and stick on the membranes and will also become a gluing agent to stick other things like hair, gutka pouch fines, or bottles or plastic.
Hello, Sanjeev, I think we have missed you.
Yeah,
Things like that. So grease, I think, should not be a problem.
Okay.
Yeah.
Sanjeev,
Yes, Mr. Ramkumar.
Yeah, Sanjeev, we have this question from Arun Kumar Agarwal. He's asking, what is an economical MBR
I think
size?
I got some connection issue. Yeah. See,
So
nowadays, MBR, again, I say, MBR, nowadays, domestic MBRs are also available. People will talk about MBR even for a small plant of maybe 5 kiloliters per day. I've seen those kind of MBRs where there's an aeration tank and there are some MBR sets coming from maybe China, and people just suck permeate and say this is MBR. So if you talk about that, even 5 KLD per day MBRs are available in India.
Okay.
But if you talk about 2 MBRs, the way I was trying to teach you, it doesn't make sense to make a plant MBR if you don't have a capacity less than at least 500 meter cube a day.
Okay, so one more question from Wasim is that normally membrane replacement schedules are adopted in either a municipal or an industrial effluent scenario. Does it depend on the type of an MBR membrane considered?
No, absolutely not. That's why I always say, see, the membranes are manufactured by one of the best peoples. Years of research, lots of knowledge. But Shirodkarji, I give that answer in a larger perspective. What is the problem in industrial municipal plant, if you talk about? So most of the time people will say lack of knowledge, less training, no care, no proper manpower given, no proper education. In that environment, would you sell MBR? I would never sell. Because the knowledge level and engineering level and the process know-how level has to be upgraded to such a level. So government has come up with something called hybrid annuity model. Where India's premium companies, for example, I should not name, but the discussion that talking about VTech, Wabax, and Adani's, they are putting up the projects. Now, if they are using MBRs, I'm okay with that because it's on a hybrid annuity model. They have all the manpower and resources to put the right people to operate the plant, which is 100% automatic. So, not diverting from the topic, but domestic still, I will feel that in India we may not require the MBR, for sub-fuel. But industries, yes, there will be a lot of advantages to industries if they shift to MBR because less manpower and better controls.
So Pawan is asking this question: any specific power consumption cost of MBR and ASP?
See, ASP will definitely consume less power in comparison to the MBR, which goes towards something called, a technical answer. I am not sometimes giving marketing answer. I'm sorry to disappoint people. Because if you keep on keeping the sludge with you and look for a lower sludge volume, that the last word which my colleague says, endogenous respiration. You have to give oxygen for that. And who will give that oxygen? Air blower. So the air blower will give that oxygen for endogenous respiration, and therefore MBR plants will have more energy consumption technically. But if you want to prove on a piece of paper to win a bid something, then you do whatever you want. Biology-wise, MBR will consume more oxygen than in comparison to a conventional activated such process.
I'll take one final question, Sanjeev. Henry
Please.
Daniel is asking this question. There are some manufacturers who offer microfiltration and ultrafiltration options for MBR, which is preferred when it comes to effluent treatment.
Again, I'm saying you, this microfiltration means we are talking about the pore size of around 0.4 micrometer. So, and ultrafiltration means we are talking about much more finer. So both are excellent because 0.4 micrometer is made by Mitsubishi. It's not an ordinary company. Come on, they are very, very good people. And 0.01 micron is made by Suez and similar kind of companies. So they are ultrafiltration. What happens is if you are looking for treated water quality perspective or your cleaning strategy perspective, sometimes if you feel that my effluent is such that I would require lots of cleaning. So this effluent next project when I'll go towards MF.
So we have a
then I'll say it is a sensible decision because
Sanjeev, we have a request from Pakistan if you can suggest any quality manufacturer and a local installer there. So I would leave it to you later to maybe answer this question. So we have Mr. Kondala Rao who is asking, under what circumstances would you prefer MBR technology for municipal wastewater treatment plants?
I will say once again, municipal sewage treatment plants, when the future goal is sustainability, where the government recognizes that funds will be given for to you one time, you make your treated water quality beautiful, do a reverse osmosis on that particular water, convert it to industrial grade water, sell it to some industry at 150 rupees a meter cube, work in a municipality like a power plant. So suppose somebody puts a power plant of 10 megawatt. What he wants to do, he wants to sell power so that he can upgrade his power plant from 10 megawatt to 20 megawatt. And what is municipal business? You take funds from government today. After 15 years, you say, sir, I want fund again for next 15 years. This is not a good idea. So unless you are investing money towards a sustainable future to produce water out of wastewater, the word I've used, water, treat it like a daughter, pure, pristine, make beautiful water, give it back to the industry and charge the industry. If you're not doing that, there's no point investing into municipal wastewater treatment. If you have to treat and then throw into Ganges. So there's no point you make MBR and throw the water back to the Ganges. There has to be a sustainability model. I do not support this government of India's hybrid annuity model because that aims at treating the water and putting it into Ganges. I feel like my money goes in Ganges.
So thank you, Sanjeev. Thanks for this wonderful session. We will share some balance questions that we have and I would request if you could find some time to answer them, please.
Perfect. It would be my pleasure to answer my colleagues. Thank you very much.
Thanks, Sanjeev. This brings us to the last session that we have today. Mr. David Bromley, Chief Executive Officer of DBE High-Tech from Canada, is going to talk about RSL membranes, a technological breakthrough in membrane technology, and is going to present a case study of treatment of produced water in an oil and gas industry. Mr. Bromley had to leave for a minor surgery today, and hence he was kind enough to record his presentation to us and send it to us last night. So over to you, Ram. Can you play David's presentation, please?
Good day. My name is David Bromley, and I am the chairman of DB High-Tech located in Vancouver, Canada. I'm just going to bring up a screen share. There we go. So thank you. I also want to recognize the co-authors to this presentation, Dr. George Shimizu and Dr. Osun Ulama Tamiwa, both from the University of Calgary. So I'm going to present to you today a new membrane technology, a distinct membrane technology that is patented. It does not rely on the typical barrier type of separation of solids from the fluid, from the water, but it does rely on the manipulation of the electric double layer around those suspended solids and colloids. The presentation will compare the RSL membranes to conventional low pressure membranes. And figure 1 actually is a photograph of a membrane bundle, an RSL membrane bundle. This is a titanium tubes that were used in this particular photograph, but normally we use polymeric tubes. So we've categorized the conventional membranes into 2 categories. And when I say conventional membranes, these are membranes that separate suspended solids or colloids from water. So the first category is the conventional low pressure microfiltration, ultrafiltration membranes, and we all know those very well. And the second category is dynamic membranes, which rely on the coating of a powder, typically a diatomaceous earth, on the membrane surface, which then creates a filter cake. Both of these categories rely on the pore size of the membrane or the pore size of the filter cake on the surface of the membrane to physically separate suspended solids and colloids in the water. This is known as barrier filtration type technology. RSL membranes are not a barrier filtration technology. Instead, they rely on the formation of a strong electric double layer to cause repulsion of colloids and suspended solids from the surface of the membrane, and then subsequently the collapse of the electric double layer to cause attachment. And the science behind this technology is the well-known Dlvo Theory, which is the acronym for the scientists who developed the theory: Dergewin, Landau, Verwey, and Overbeek. The RSL membrane technology relies on creating, and in a highly ionic environment on the surface of the membrane, by using a replaceable powder skin layer, RSL powder. There are 3 steps to the operation of RSL membranes. The first step is to apply the RSL powder. This takes about 5 minutes. It's done in situ. In other words, we do not pull out the membrane tubes from the membrane housing and put the powder on the tubes. Instead, we do everything within the membrane housing in a submerged environment. The second step then is to filter the water we're going to be treating. And this cycle will take anywhere from 2 to 30 hours. But for most wastewaters and waters to be treated, it's in the 4 to 8 hour time frame. And finally, the third step is once the transmembrane pressure gets to 70 kPa, we will backwash the RSL membrane, backwash off the RSL powder from the membrane, and also vacate the entire housing contents. And this takes about 1 minute. We have had a number of field pilot tests, but there were 2 tests that we were very interested in, and as a result of that, wanted to do a deeper assessment as to the premise behind the technology. The first pilot compared the RSL membranes to Veolia's Ceramem membranes, and many of you know that these Ceramem membranes have a silica carbide skin layer. This was a 1-year pilot test. It's done by a third party. And it showed consistently that the RSL membranes had a 10-fold improvement in flux rate compared to the Ceramem membranes. The second pilot, worth noting, was a separation of colloidal oil, emulsified oil, in a refinery wastewater. The RSL membranes performed very well with very high concentrations of emulsified oil. Figure 2 is the water samples from that particular test. And this was the water that actually was going into, lots of free oil in this, was going into induced gas flotation system. This is the effluent from the induced gas flotation system. A very milky water, all emulsified oil. And this is the permeate after the RSL membranes. After these pilot tests, we developed a test program to prove the hypothesis that we could manipulate the EDL, the electric double layer, and cause repulsion and attachment as the method of solid and colloidal separation in the water. The key steps in the testing were to evaluate or compare the different powder configurations that we could apply, creating a different environment, ionic environment. These powders were then evaluated based on a data plot of transmembrane pressure versus turbidity versus time. The tests were undertaken using synthetic wastewater containing a kaolinite clay, where we added 4 grams of clay per 20 liters, and then we mixed the water vigorously. The clay mixture was allowed to settle for 12 hours, and then the supernatant was used as the feed water for the test. And typically the feed water turbidity was in the 30 NTU range. The reason we wanted to use the supernatant is because we truly wanted to have suspended solids in the feed water that we were testing. The membranes were operated at a constant flux rate of 350 liters per meter squared per hour. The membrane tubes tested were both titanium and polymeric. The pore size of the membranes ranged from 3 to 8 microns. And other than the RSL powder, no other chemistry was used. And this is very consistent with our normal operation of field systems. We only use the RSL powder for treating the water. So let's look at the results. So the results, we actually did 3 plots. So figure 5 is the plot of the RSL membranes, and we plotted transmembrane pressure, turbidity over time. The blue line being turbidity, the orange brownish line being the transmembrane pressure. And we compared this plot to the conventional membrane. So figure 3 is the conventional low pressure membranes, microfiltration, ultrafiltration type membranes. And as you can see here, these are just typical results. These were not an actual plots. But what we were showing here was that, look at these type of membranes always get a very consistent turbidity level throughout the filtration cycle. They're high quality turbidity, so perform very well in that regard. And then you get this kind of Z pattern on the transmembrane pressure. You'll start off with an original transmembrane pressure. It increases on a linear basis to a backwash. In this case, we looked at a backwash every 15 or 16 minutes. You'll bring the transmembrane pressure down. It never goes back to the original. In this case, we also show here that we're doing the 3 cycles of backwash, and then we get to the 4th cycle, so roughly 1 hour time frame. We actually do a chemical enhanced backwash with some type of oxidizing agent. And as a result, we get a better recovery on transmembrane pressure, but never back to the original. And you can see the gradual deterioration of the transmembrane pressure for each cycle. Eventually, we'll get to a point where we have 200 to 300 kPa of transmembrane pressure, and then we would do a clean in place, which, as you know, is an acidic or a caustic wash. The second conventional category of membrane was the dynamic membranes we talked a little earlier. In this case, this is a very simple plot where, as the filter cake builds on the surface of the membrane, the quality of water improves, the turbidity improves. Conversely, as that filter cake builds, there's a linear increase on the transmembrane pressure. So you get this type of X plot. So when we then looked at the RSL membranes, we saw 2 zones occurring as far as the plot was occurred. First of all, very consistent, high quality turbidity water throughout the filtration cycle itself. Similar again to the conventional low pressure UF and MF type membranes. But very interestingly, we got some great turbidity levels in the initial, what we call zone A. It was as low as 0.04 NTU. So very high quality water. But more interesting is that our transmembrane pressure during this first part of the filtration cycle was essentially 0. And that is, over about 40% of the filtration cycle, 40–50% of the filtration cycle, we get this very low transmembrane pressure. Then all of a sudden there's a spike, and that spike is 15 to 20 kPa. And as a result of that, we then get this asymptotic increase in the transmembrane pressure up to 70 kPa, where we would then backwash. So let's look at what we see as conclusions. The conclusions, the fact is that the RSL membranes operate for a significant portion of the filtration cycle with a transmembrane pressure close to 0 kPa. And this can be explained by the manipulation of the electric double layer on the colloids. The Dlvo theory teaches the impact of the ionic environment on the strength of the electric double layer. Because of the intense ionic environment caused by the RSL powder itself, the colloids are repulsed from the surface of the membrane. As a result, during the zone A time frame, the membrane surface is not fouled, and the permeate can flow freely through the powder and the membrane tube. And remember, the RSL membranes have a very large pore size, so there's no hydraulic restrictions. The RSL membranes operate in a dead end mode, and the repelled colloids concentrate in the membrane housing. Eventually, those colloids leak into the RSL powder, and the EDL, the electric double layer around those colloids, collapses. Van der Waals forces become dominant. The colloids then aggregate and attach to the RSL powder. The pressure then spikes and increases asymptotically. This is the zone which we call zone B timeframe. RSL membranes are distinctly different from all other membranes. The ability to manage the electric double layer on colloids facilitates high flux rates at very low transmembrane pressures. Thank you, and I look forward to your questions.
This brings us to the end of the session for the season 2, episode 1. As I said at the start, that unfortunately David had to leave for a surgery, so he is not there to answer any questions after his session. Ram, can we have the slide up, please? Ram? So as I said at the start of the session today, that we are extremely privileged to have Canada as a host country for the season 2 of the IWET series, and we will be having every episode a Canadian company sharing their expertise and innovations. And in case we want to connect with any Canadian companies or to leverage the Canadian capabilities in the water sector, you could speak to any of their trade commissioners, who are mentioned in the email, whose emails are given below. We have Yasmin in West, we have Saroj in North, and Mr. Ramesh in the South. You could connect to any of these trade commissioners to know a bit more about the Canadian capabilities in the water and the wastewater sector. So with that, I bring the episode 1 to a close. I would like to thank all our speakers for taking time out of their busy schedules and sharing their knowledge and insights with us. And most importantly, a big thank you to all the attendees who have patiently listened through the sessions and participated through their questions. So thank you all very much, and we will be sharing the dates of the episode 2, which is in November, for the IWET series very soon with all of you. So thank you, and with that I bring the session to a close. Thank you.